Alrighty, get a couple things out of the way. I'm very ADHD. In fact, I clinically diagnosed with it, so I do tend to drone on about little random tidbits and shit that makes it difficult to get my point across. To get my main point across right now is primarily to show you the current handling abilities of my power supply. Most of the noise you're hearing is actually coming from that, my linear power supply. The fan in there is ridiculously loud. So, to get this across, that right there is the output of our inductor. We're feeding at 14 volts, we're getting 22.7 out. We're going to put it under a heavy, probably 9 or 10 amp load on the input. We're measuring current on the input. I don't care about output current. We care about input current because that's what determines the saturation of our core. Now this right here is a high, this current core handles 80 amps continuous, saturates 120 amps, operable between 1 kilohertz to a megahertz. It's made by Synnex Meter. It's a planar core. No, I don't know the part number. I might link it below, I might not. You can easily look for it on DigiKey. They make tons of them that look just like this. They're ridiculously tiny too, and they handle a lot of current. This is on a power supply that's limited to plus or minus 5 amps. I have them tied in parallel, so it gives me 10. That's a pretty heavy load. It's 9 amps, like I said. Ooh, that's a pretty good voltage regulation. I can guarantee you all that loss that you're seeing there is most likely coming from the wire. I mean, if you look at it, I'm using 16 gauge wire everywhere, 16 gauge, and that's not really meant to handle this much current. Let me put my camera down for a moment so that way I can actually handle what's going on here. Okay. So as you can see from the waveform, our inductor is nowhere near saturation. We have a nice, strong square wave. So our knee, remember, if I was hitting current saturation, our knee right here would be diagonal. It would actually be getting narrower and narrower. And it's not. Yep, it's skipping pulses, which is what I have it designed to do. It saves power when you're not using it or under a very light load. Increases efficiency. This power supply is anywhere between 90-95% efficient under even a 10 amp load, which is surprising as shit because I wasn't expecting that. We're going to increase our output voltage ever so slightly. That way we can go ahead and okay, I don't want to go any higher than that. You're seeing a 10 amp load. It's 140 watts right here, right now. Nowhere near current saturation. So I'm not kidding when I say I actually have a power supply that can handle the amount of current. Let's see. We got our trusty thermometer here. That's extraordinarily cold. Let's actually measure at the chip itself. That's 107 degrees max. Let's go ahead and see what the diode is. About the same. It's 106 max. That's very good. Let's go ahead and try that again with a fresh max reading. That's very good. And this is under a 10 amp load. This thing's handling like a champ. This will let you know the MOSFETs, they can handle about 40 amps pulse at 50% duty cycle, which I'm operating nowhere near that. I'm actually operating close to about 2%. We can actually determine duty cycle right now, actually, by looking at the pulse width. That's 291 kilohertz. So I'm operating at 50% duty cycle, like I thought. I'd probably say, hold on a second. No, I'd probably say it's close to about 45% G cycle. Irrelevant. It's operating close to 50%. Each one can handle 40 amps at that kind of current rating. Sorry, that kind of frequency, and that's a ridiculous amount of current. Those two will handle more current. The fact that inductor would explode long before those MOSFETs would ever, get hot enough to cause damage to themselves. I can touch it. It's actually pretty warm because we're letting it sit here to show a load test. Now, let you know, the temperature in the room is 87.5. Oh, my bad. So you got a max reading of 122 right there. Oh, yeah, it's probably gonna get a little hot. Those are resistors, by the way. Yeah, they are. This is the resistor I'm reading. It's irrelevant. Those can get up to 200 degrees for all I care. We're just gonna let it sit here. We are running into problems, as you can see. I am beginning to burn the table because of the heat from my load resistor here. Load resistors, excuse me. I'm gonna have to shut this off soon, primarily because my load resistors are not meant to handle more than 50 watts apiece, and I'm pretty much exceeding that by about 25 watts per load resistor, which is, I'm impressed. I'm seriously impressed. And look at the road regulation it's sucker, 23.2. Oh damn, the connectors are rather hot. Yeah, it's a 0.8 volt drop. I can guarantee you that drop is caused because of all the wiring here. And I mean, this wiring is getting really friggin' hot. So we're dropping current, we're dropping voltage primarily because I'm using 16 gauge wire on the input. So I'm gonna probably be dropping like half a volt down to a volt on here, which would make sense here. If I was using 8 gauge cabling everywhere, our output voltage wouldn't change at all. So yeah, it works pretty well. When everything's all said and done, it'll probably be inside of a chassis that looks like this with binding posts on the end. And I will most likely not be using that kind of a heatsink. I'm going to be using the chassis as a heatsink because it's 12 inches long, man. 12 inches by 5 inches by 3 inches. They're dirt cheap. You can get them on Alibaba. You do have to buy them by a minimum quantity in the poundage, sadly, in order to get them. I ordered a sample for free, and they charged me 20 bucks shipping for it. Awesome, free sample. Anyway, so you saw I handle 10 amps. We weren't getting hot, barely at all. Our diodes are never going to get very hot. They're not going to be. Voltage drop on these diodes is special. They're all made by Ixis, and they have about a 0.4 volt drop. So even at our 100 amp load, they got to dissipate 40 watts of heat. And because there's two of them that's spread apart, so that's actually 20 watts a piece that I have to dissipate. And that's under 100 amp load, mind you. So it's 1500 watts to probably about 150 watts of heat that we're going to dissipate. So, we're getting efficiencies around 80 to 85% to 90%. And that's very, very good. Very good, mind you. And almost all the losses are going to be, strictly speaking, within those resistors here and the voltage drop on the diode. There's no way I can get around that. That's just a standard physical limitation of electronics. There's a voltage drop on the dial, bro. I can't do shit about that. So it seems like this circuit's actually fairly well made. It's being fed properly. A couple of design notes you're probably going to see. And that's mainly one. I do like Marathon. That's my favorite video game. I left solder traces off. My solder mask off by accident. This is only a proto board. It's actually a 4-layer board with multiple grounds but sandwiched in between them. This is a reduced inductance and straight capacitance, which is why I'm getting such a clean output. If you haven't noticed, I'm getting no ringing, and it's very difficult to design for.